In this video, we would like to prove a Hölder's inequality. The inequality is of this form that you see here, or in this form, and it basically means that the norm of the product of the two functions f times g in L1 is bounded by the LP norm of f times the LQ norm of the function g. So we write the proof of this. This is one of the most popular inequalities in analysis, and it is used very frequently, most of the times in PDE analysis, and it's also one of my favorite inequalities. So in order to prove this, we need to use first the Young's inequality. The Young inequality is this one here. I will use it directly. I won't use a proof here. I have made another video for this, for the proof of this inequality, where here the indices P and Q satisfy this relationship. The inverse of 1 over P plus 1 over Q is equal to 1, and P and Q belong to this interval. Now we pick for A to be the f over the norm of f in LP of omega, and B, beta, g over the norm of g LQ of omega. So we pick A and B, and then we replace A and B, A alpha and beta, back to Young's inequality. So we will obtain the following bound. This is bounded by A to the power of P over P plus B to the power of Q over Q. Let's make substitution. This is f over norm of f LP of omega, g over norm of g LQ of omega, and this is bounded by this is 1 over P, and here you have f to the power of P and the norm of f in LP to the power of P plus 1 over Q, g to the power of Q over norm of g, the LQ norm to the power of Q. So what we have here is that we have the product f times g in absolute value, and in the denominator we have the product of the two norms of f and g, and of course we can write the right hand side of the inequality is the absolute value of f to the power of p, and we also write the norms in the denominator. Now what we have to do is integrate over omega, and when we integrate over omega, in the numerator we get the norm of f times g in L1. Of course the denominator remains the same, and at the left we have 1 over p. In the numerator we have the norm of LP, the LP norm of f to the power of p over the norm of f in LP to the power of p plus 1 over q norm of g LQ to the power of q over g LQ to the power of q. Of course, now we notice that at the right hand side we can simplify the p and the q norms. So we have the L1 norm in the numerator over the product of the two norms of the function f and g. And at the right hand side we have 1 over p plus 1 over q. But this one is equal to 1. So we obtain that f times g norm in L1 over norm of f Lp omega g Lq omega is bounded by 1, and by rearranging the bit this inequality, we have that at the left hand side the norm of the product of the two functions in L1 is bounded by the norm of f in Lp of omega times the norm of g in Lq of omega. If p equals q equals 2, we have this following corollary, that this norm here in L1 is bounded by the norm of f in L2 of omega times the norm of g in L2 of omega, which is the so-called Cauchy-Schwarz inequality. This is one of the most useful inequalities in analysis of PDEs.